Okay, so it's a great pleasure to have Rune Haugseng from Norwegian University of Science and Technology. Thank you very much for accepting our invitation. So we are going to hear about higher Morita categories.
Okay, yeah, thanks for inviting me. I thought I would say something about higher Morita categories and connections to TQFTs, but let me start with kind of the most classical kind of Morita categories. So let's say that R is some commutative ring. Then we can define a category by taking the objects to be associative R algebras and the morphisms from A to B, or these are two associative R algebras, to be AB bimodules. And here, if we want to stay within the world of ordinary categories for now, we should take isomorphism classes of bimodules, because we want the composition of bimodules. So if I have M an AB bimodule and N a BC bimodule, I'd like the composition to be given by taking the tensor product over relative tensor product over B of M and N. And that, of course, in order to be strictly associative, we have to take this quotient by isomorphisms, since it's only associative up to isomorphism. And then the identity of an object A will be A viewed as an AA bimodule. And so we might call this the Morita category of R, because two algebras A and B are isomorphic in this category if and only if they are Morita equivalent. Isomorphism in this category exactly corresponds to the choice of an AB bimodule M and a BA bimodule N, such that if I tensor them over B, I get an AA bimodule that's isomorphic to A, and if I tensor over A, I get a BB bimodule that's isomorphic to B, which is one way of saying what a Morita equivalence of rings is. Right, so we can upgrade this ordinary category to a 2 category by adding in bimodule homomorphisms as 2 morphisms, and moreover we can upgrade it to a double category by also adding algebra homomorphisms as another kind of morphism. So I should maybe say what I mean by a double category. So at least heuristically, a double category is a structure where we have objects, draws points, and then we have 2 kinds of morphisms between the objects, which we call the vertical and the horizontal morphisms. Which we draw accordingly as either vertical or horizontal arrows. And then we have a two-dimensional structure, which is a collection of squares. So they have a boundary that looks like this. So the boundary of the square gives you two horizontal morphisms and two vertical morphisms whose sources and targets match up like this. And we should be able to compose, well, we should be able to compose the morphisms, and we should be able to compose these squares both vertically and horizontally.
Well, there seems to be a question about double category. So is it equal to bicategory? That's the question.
No, a bicategory is, so a bicategory, you would have one type of morphism and you have two-dimensional, like the two morphisms, which kind of look like this. So there is no, like, there's you don't have a square, you just have one kind of morphism and then two morphisms relating parallel pairs of those. What distinguishes a bicategory from a two category is whether the composition is strict or only up to isomorphism, which I haven't said anything about for double categories yet, because you can make the same kind of, you can make several versions of what a double category is, depending on whether you require the composition to be strictly associative or associative up to a coherent isomorphism. So the composition should be unital, or the compositions of all the both horizontally and vertically should be unital and associative. And then you could try and make it strictly associative, but in examples we typically want it to be weak or up to coherent isomorphism in at least one of the two directions. Right, and let me remark that you can extract a two category by, like, for example, forgetting forgetting the vertical morphisms, and so you only keep squares of the form, well, this, like this, where the vertical morphisms are identities. So a double category has an underlying two category, or maybe a bicategory if we made it just weakly associative. So, and going back to this example of the Morita category, there exists a double category, which we might call, well, I'll call it more one odd for ordinary, during R, where, well, objects are associative R algebras. The horizontal morphisms are bimodules, like with composition being a relative tensor product. And so here it has to be weak in this direction because the relative tensor product is not strictly associative, but only associative up to isomorphism. So that's a good example to think of to see what this weakness like kind of comes from and why we need it. Whereas the vertical morphisms are algebra homomorphisms. And so those do compose in a strictly associative way. So if we want, we can, this is an example of a double category that is strictly associative in one direction and only weakly in the other direction. But that's kind of only relevant for the moment. It's later on we're going to make everything as weak as possible everywhere. So, right. And then we have squares. So square is supposed to be related to homomorphisms. So the boundary of the square will be an AB bimodule and then a homomorphism and two homomorphisms in the vertical direction. And then we have an A prime, B prime bimodule, M prime. And the data of the square is a bimodule homomorphism from M to M prime regarded as an AB bimodule via the maps alpha and beta that we specify. And right, so this is the double category, and as I mentioned, this has an underlying, well, I'll just say two category. I guess I should, it's really a bi-category here since it's weak, but yeah, it's an underlying two category, which I might call lowercase more one odd of R. And let me mention that this is actually symmetric monoidal. And you can make a symmetric monoidal structure on the double category as well. And this seems to have been first written out in detail by Mike Schulman in 2010. Right. So the point now is that we have this structure, this two category, and from this we can extract, this contains a lot of algebraic information about associative algebras over R. So for example, we can extract, well, we have the notion of Morita equivalence as equivalences in this two category. Morita equivalences of R algebras as the equivalences. We can also extract algebraic invariants like the Picard group of an R algebra A. That's just the group of invertible endomorphisms of A. We can extract the Brouwer group of R as the group of isomorphism classes of invertible objects using the symmetric monoidal structure. So otherwise, an invertible object is an object A such that there exists another A prime that is inverse to it in the sense that if I tensor them together, so I take tensor over R, A and A prime, then that's equivalent to the unit R, but this is a equivalence in the sense of Morita equivalence. So this is one way of saying what an Azumaya algebra over R is. They're exactly these kinds of invertible associative R algebras. And that agrees with the kind of maybe the most classical definition where R is a field and you consider central simple algebras over the field. This is like a more general version of that. So, right, so this was kind of the classical Morita category. So the work that I want to talk about today is the goal is to understand a more homotopical version of this construction. For example, we might want to replace these ordinary R algebras with say associative differential graded algebras. So algebras and chain complexes of R modules, or more generally, you might consider these kinds of structures for ring spectra in the sense of stable homotopy theory. And the one motivation for wanting to do that is to understand more fancy homotopical versions of invariants like this. You know, if you upgrade from like the Brauer group of R of commutative algebra R is quite closely related to what is it? The first étale cohomology group of R with GM coefficients. But this relationship is much closer if you replace the ordinary Brauer group by the derived Brauer group, which amounts to passing from ordinary associative algebras to DG algebras. So that's the theorem of Twin and of Ancho and Gepner, that if you look at the derived Brauer group, then it's basically always isomorphic to this étale cohomology group. Another motivation comes from topological quantum field theories, which I'm going to say a bit more about later on once I've talked about try to say something about what I mean by this homotopical version. So I'll try and say something about going from double categories in the sense I talked about them now to double infinity categories.
Sorry, before you, yeah, okay. Just something. So for the Brauer group, it seems to be like a three-categorical thing rather than like you have rings. You can have associative like bialgebras and bimodules between them and so forth. You know what I'm saying? Like you have, you can consider this thing where you have different rings and bimodules between them, and then bimodules between the bialgebras and things like that. So that seems the most natural place to do this, because you're tensouring like modules. Sorry.
I'm not sure I understand the question. I mean, you can.
Yeah, I'm saying like for
when vary the ring, but that's not really the same as saying you have. I don't think you get a higher. Well.
But you're using the monoidal structure, so in some sense, that is a higher thing.
Right.
So, yeah, okay.
I mean, there are like, I mean, I'll say a little bit later on about other generalizations where you want to look at, you're still taking the two category of associative algebras. You could look at the infinity n category of EN algebras, and then you get a sequence of kind of d-loopings of the classical like the Brauer group of E1.
Okay.
Yeah, so I thought I would try and say a few words about infinity categories and infinity n categories, and I don't know I find it's impossible to really judge what the audience is like for these online talks. So I might be saying something everyone's heard a million times before. I might be saying way too little because, I thought people had heard this before, and I apologize if I just got it completely wrong. But let me just at least mention the kind of vague idea that an infinity n category is supposed to be a structure where we have I-morphisms between I-1 morphisms for all I, but they should be invertible if I is greater than n, and composition should only be associative up to a coherent choice of invertible higher morphisms. So there are, you might try and make sense of this as some kind of complicated algebraic structure, but one key, we could call it a conjecture or an assumption of Grothendieck, the homotopia hypothesis, is that if we take n equals 0 here, so we look at infinity zero categories, which are usually called infinity groupoids, then those structures should be the same thing as topological spaces considered up to weak homotopy equivalence. So if you cooked up some kind of algebraic notion of what this kind of data should be, you could regard this as a conjecture you wanted to prove about that description of infinity groupoids. But another thing you can do is to just take this as a starting point. So you basically view topological spaces as infinity groupoids, or usually another more combinatorial model of the homotopy theory of topological spaces, such as some additional sets. And then, so you take that as your starting point, and then you build a theory of infinity categories, infinity n categories, on top of this homotopical version of infinity groupoids. And so this turns out to work very well, and this is kind of the idea, that's the starting point for these homotopical models of higher categories that have, I guess, revolutionized the subject, you could say, and made it a theory where you can actually work and prove things. So we can take this in some sense as a definition of what an infinity groupoid is. Build a good theory of infinity n counts on top of it. Okay. So now I'll just assume that we've done that. We've built this theory of, well, at least infinity one categories. Maybe I'll also mention, following Lurie, I'll use the abbreviation that an infinity category is an infinity one category. So then I want to tell you what a double infinity category is supposed to be. So I can make the following general definition of a category object in an infinity category C with finite limits is a simplicial object, so a functor delta op into C, say x, such that xn, the value at the bracket n, is isomorphic to an iterated, equivalent to an iterated fiber product of copies of x1 and x0 via the maps in delta. So delta is of course the category of non-empty ordered sets, 0 less than or equal to 1, less than 1, less than so on up to n, and so I can look at the inclusion of the two objects I minus 1 and I in bracket n, which is the ordered set 0, 1 up to n, and also of the one element set, just a single object. So through these maps, I get maps from xn to all of these things, and I'm saying that should exhibit xn as this iterated fiber product. So why is this a category object? Well, if I take C to be just the ordinary category of sets, then these category objects are just the usual notion of category. I think of x0 as the set of objects in a category, x1 as the set of morphisms, and then I have between x0 and x1, I have maps like this, where these maps give me the, so I think of as the source and target of maps for the map that assign a morphism to its source and target, and then this section is the one that assigns identity maps to each object. If I look at this fiber product of x1, two copies of x1 over x0, then this is the space, the set of composable pairs of morphisms. So I have two morphisms, and the target of the first is the source of the second. That's what this fiber product says. If I think of the maps from x1 to x0 as assigning sources and targets, that's now isomorphic to x2. And then I have another map from x2 to x1 that I didn't use in forming the fiber product, which gives me this is the middle face map d1, and this gives me the composition in my category. And then you can work out that the condition for x3 and the fact that a square of maps from x3 commutes gives you the associativity. Like if I look at 3, there are 2 inclusions. Well, I can. I think of this as the set 0, 1, 2, 3, and this square of inclusions commutes, and if I translate that into the condition for x, I get a commutative square that encodes associativity. Like I have a map from x3, and the 2 ways of going around the square are the 2 different ways I can compose 3 morphisms. And well, so if I just take C to be set, or any ordinary category, actually, I didn't need this whole structure of the simplicial object. I could have just looked at the subcategory where I only have the objects of size less than or equal to 3. But that's no longer true if I work with an infinity category. right. Let me say if I take C to be cat as just an ordinary one category, then I get the strict notion. If I look at category objects there, I get the strict notion of a double category. If you work out what the structure is giving you, then I can think of X0 as the category of objects and vertical morphisms in the double category. And I can think of X1 as the category of whose objects are horizontal morphisms and whose morphisms correspond to squares. And so that's the strict version. But if I think of cat, well, I can also think of cat. Well, there's a 2-1 category of categories. Where I take categories, functors, and naturalized morphisms. And if I view that as an infinity category, and consider this definition of a category object there, that amounts to saying that instead of saying that this should be an isomorphism of categories, I'm asking for it to be an equivalence of categories. Then that corresponds to a weaker notion of a double category. Well, right, so that's one way of describing double categories as category objects, but we can also now upgrade from categories to infinity categories to get a notion of double infinity categories.
Sorry, can you say in which sense this is weaker? Like, will it be like a weak in one direction, or
yeah.
it be because of the map here from xn to, so that will be in the horizontal direction, if I understood correctly. Like,
Yeah. So you want x2.
yeah,
This
x2.
map is just an equivalence of categories, so it's not. And I guess, well, there are several. You can also weaken it by saying that instead of asking for a functor of one category, you want it to be what do they call them? A pseudo functor of 2 categories, and that's kind of also baked into this. So yeah, I don't want to make this completely precise, but yeah, you get a good weak version of a double category, but it's some work to like connect up these kind of simplicial versions to the kind of diagrams you'll see in papers on like bicategories and weak double categories. So, but morally it's the same. So yeah, now I can take target C to be, well, also S, the infinity category of spaces or infinity groupoids. So we're replacing sets with spaces, sets being kind of the infinity version, spaces being kind of the infinity version of sets. We might expect this to give us a version of infinity categories, and that's true. This definition gives exactly the Siegel spaces of RESC, which give one model of infinity categories. More precisely, it's a model of the algebraic structure of infinity categories. And then there's one further step, because you have to think about what equivalences should be between these. Namely, they should be fully faithful and essentially surjective morphisms, and you want to invert those. And that will then relates to the theory of complete Siegel spaces and so on, but I don't want to get into that. And finally, I can take C to be cat infinity, the infinity category of infinity categories. And then I get here a notion of double infinity categories. As these simplicial objects in cat infinity. And inside of those, we can find infinity 2 categories as those double infinity categories, say X, where the 0th category is actually an infinity groupoid. No. This is the definition of infinity 2 categories due to Clark-Barwick. And again, there is this question about completeness, inverting fully faithful and essentially surjective morphisms. But yeah, let me not say anything about that. Okay, so this is at least a sketch of a definition of the kind of objects that we want to define in this Morita setting. So, like what we want is, well, given a reasonable symmetric monoidal infinity category, we should have a double infinity cat. I'll call it more 1 of C, where the objects are supposed to be associative algebras in C, and morphisms are bimodules, and so on. So if I take C to be the ordinary category of modules over a commutative ring, I should recover the first version that I looked at, the ordinary Morita 2 category, while the more homotopical version I would get by plugging in C as, say, the infinity category you get by inverting quasi-isomorphisms between chain complexes, or say modules over some commutative ring spectrum. So I haven't told you what a symmetric monoidal infinity category is or what an associative algebra in it is. And I don't think I want to do that, because there's kind of there's like several layers of formalism you have to introduce to define that. But I can at least tell you how you can define this in the case where the tensor product we're looking at is a Cartesian product, since then we can define what an associative algebra object is without having to introduce the notions like infinity operands. So then I can define an associative monoid in C. Well, I can define it in terms of the previous definition as a category object X, such that the 0th object X0 is the terminal object. Or what that amounts to is that I have a simplicial object such that Xn is equivalent to an n-fold product of X1, where not where, but via the inclusions of I minus 1I into bracket n. So, I mean, if you go back to the explanation I tried to give for why these category objects look like categories, you can similarly explain why this is an associative monoid. Now, this x0 is just a point. And so the only interesting map here is the unit map, which gives you the map in this direction, which gives you the unit for the monoid. And then now x2 is equivalent to the product of two copies of x1. So this map gives you a multiplication from x1 cross x1 to x1. And then as here, this square tells you that this multiplication is associative, and so on. And we can describe in a similar way what a bimodule is. So instead of looking at delta, we look at delta over bracket 1 up. So it's good to think of objects of this category as sequences I0 up to In, where I0 is less than or equal to I0 less than or equal to In less than or equal to 1. So this sequence just encodes the values of a map from bracket n to bracket 1. And then the condition to describe bimodules is, well, let me call it a delta over 1 up monoid as a functor delta over 1 up to C such that, say M, such that the value at this sequence is equivalent to a product of the value at the product of the values at the pairs I0, I1, I1, I2, and so on up to In minus 1, In. So what is this encoding? This gives two associative monoids. Say A, which is given by M00. If I just look at the subcategory of delta over 1, where all of these values are I0 through In have to be 0, then I get a copy of delta, and that I can, restricting along that, I get an associative monoid like here. And then I get another one by just looking at those sequences that consist entirely of ones. And finally, I get an AB bimodule structure on M01. So I can take, if I wanted to define this double category, I can take more1C0 to be the category of associative monoids, and more1C1 to be the infinity category of delta over 1 up monoids in C. And then you can describe the tensor product of bimodules using delta over 2 up, and so on. Yeah, I won't say anything more about the details, but this is one approach to defining this double infinity category. And if you upgrade it to use infinity operands, you can define it also when the product in the tensor product in C is not Cartesian. So this is one way of doing defining this double infinity category, and Laurie actually has a different version in his higher algebra, and then there is a more geometric version using factorization algebras due to Kalak and Scheinbauer. So all these constructions give you a symmetric monodal infinity category, double infinity category. Say more 1C of algebras and bimodules in C. Yeah, for C. Nice. Symmetric monodal infinity category. So to give some justification for why this is an interesting structure, I thought I would say something about connections to topological quantum field theories next.
So sorry, I've got another question. So in this more one, so this was a simplicial object. So when we think of like the infinity category of n simplices here, so that, I mean, to compare it with the usual double categorical case, that should correspond to like tensoring the vertices and mapping them somehow. Like for 2, for example, you get 2.
Well, you get three algebras and 2 bimodules, and then the composition is the gives you the tensor product.
Yeah. So yeah, okay. So simplex is simply kind of tensoring these and mapping, or
well, in n simplex you have n plus 1 algebras and then n bimodules between them. So it's and then you have the vertical morphisms between those, and then the composition is what encodes the tensoring. The horizontal composition is where the relative tensor products come from.
okay. And the condition makes sure. Yeah. Okay.
Well, I didn't tell you how you actually can define the composition in the next step here. Yeah, but that's the idea anyways, that the composition of 2 in the horizontal direction is given by relative tensor products. Right, so yeah, maybe let's see, I'm kind of running out of time, but let me just call briefly the original definition of a TQFT in a TS sense. So Tia defined it to be, or at least what he defined can be reformulated as a symmetric monodal functor from, let's say, H board n minus 1 n to C. Well, maybe I should take this to be vector spaces where by this H board n minus 1 n, I mean a category where the objects are closed n minus 1 manifolds. And so, you know, I could put various decorations on these categories and say I might want all the these manifolds to be oriented. I think that was what Tia was really looking at. Or you could ask them to have a framing and so on. So there are many different flavors of TQFTs. But I think in the interest of time, I'll just ignore that and just look at the, right here, not just look at the unoriented on one where you just look at general manifolds. Morphisms are n-dimensional cobordisms. Say you have an n-manifold with boundary, and you decompose a decomposition of the boundary into two pieces, which you think of as the source and target of the cobordism. Composition, well, since it should be a one category, I want to take these up to diffeomorphism. And then composition is given by gluing cobordisms. And the tensor product is just disjoint union of cobordisms. So, right, this is the original definition. Then you have the more fancy definition, which I guess there are a lot of names you could put here. Maybe I should say Fried at least, and then Bayes-Dolan. Then really the final version is, I guess, due to Jacob-Lurie, that a fully extended TQFT is a symmetric monoidal functor of infinity n categories from, say, board 0n to C, where this board 0n is supposed to be an infinity n category with the objects being closed zero manifolds, and in general the isomorphisms are like I-dimensional cobordisms with corners. Right, I should mention that Kalak and Steinbauer wrote out all the details of how you define this this infinity n category. Well, and again, the symmetric monoidals for disjoint union. This is probably like another very helpful introduction to TQFTs if you haven't seen this before. So sorry about that. But next we have the big, well, conjecture or partially proved theorem. So it's conjectured by Bayes and Dolan. And of course, Lurie has this detailed sketch of a proof. And then I think Sean Priest has, well, he's proved a special case of it, the invertible case, and I think he has announced a proof of the full version along Lurie's lines, but it's not out yet. And then Ayala Francis have proposed a different way of proving it through factorization algebras. There's probably a lot of other names I could put here, but what this says is that if I look at framed fully extended TQFTs, so in the definition of the bordism category, I now require everything to have framing. So appropriate trivializations of the tangent bundle plus some trivial bundle. These are determined by, well, so this is supposed to be a symmetric monoidal functor from this framed board 0n. Oh, I forgot to say that we now also have, this is the n part of the infinity n category, and after n you kind of add you add on like diffeomorphisms and smooth homotopies and so on. So you also have like the full space of diffeomorphisms between the manifolds at the top level. Right, so such a frame fully extended TQFT, say Z, this is completely determined by what it assigns to a point, which is just an object of C. And you can describe these objects that correspond to TQFTs as the fully dualizable or n-dualizable objects of C. So the original definition in a flurry of these fully dualizable or n-dualizable objects is a fairly complicated inductive definition, but I can at least tell you what it is in the first couple of cases. So one dualizable is just the usual notion of being a dualizable object in a symmetric monoidal category. So we have an object and there exists a dual object, and what characterizes this object is the dual, so there should exist evaluation and co-evaluation maps. So I'll write this for the unit. This one is the unit of the monoidal structure. So I have an evaluation map from X tensor X dual and a co-evaluation map from 1 to X dual tensor X. And then these are the properties that if I start with X and then I use the co-evaluation to go to X tensor X dual tensor X, and then the evaluation to get back to X, that composite is the identity of X. And if I start with X dual and go to X dual tensor X dual, and then go back to X dual, that's the identity of X dual. So, for example, if you look at this definition in the category of vector spaces, you recover exactly the finite dimensional vector spaces as the dualizable objects. Or more generally, if you took modules, this characterizes the finitely generated projective modules over a commutative ring. Well, okay, I see I'm basically out of time. So Laurie also shows that an object X is two dualizable if and only if it's one dualizable plus these evaluation and co-evaluation morphisms have right joints in the category C. So this is a fairly explicit characterization of two dualizability. This can actually be generalized to a simple characterization of n-dualizability which is in the thesis of Araújo, I think. So the original definition is this complicated inductive one, but you can reduce it to saying that a bunch of maps have right adjoints, and then like the unit and co-unit for those adjunctions should have right adjoints to the next level, and so on. You can't just keep going. Anyway, so what I wanted to mention in the connection with this Morita category is that Laurie shows that the two dualizable objects of this infinity 2 category Mor1C are precisely the smooth and proper associative algebras in C. So here, proper means that the underlying object algebra A is proper means that A is dualizable as an object of C, whereas being smooth is a bit more complicated. You can describe it as saying there exists a right dual A tensor A op module to A viewed as a left A tensor A op module. So I'm not mistaken, this corresponds to saying that A is finitely generated and if the classical case, I believe it corresponds to saying that A is finitely generated projective as an A tensor A op module. Okay, I see I'm out of time. What I wanted to say at the end is talk a bit about extensions of this Morita, double Morita category to kind of high dimensional versions where you look at EN algebras, and then you can generalize from looking at just algebras to looking at enriched categories, and then eventually enriched infinity N categories. But yeah, maybe I shouldn't say that's the sum out of time.
Okay, thank you very much, Rune. So are there any questions from the audience?
Yeah, so I think I asked my questions during the talk, but kind of have a, sorry, let me find my notes. So precisely what does the double categorical version enhance over the infinity to one thing you write here?
I mean, I guess in some sense it doesn't do that much. It's more like the most natural way to define the structure is to write down this simplicial infinity category, which is a double infinity category, and then passing to the infinity 2 category is kind of, you start with that simplicial object and then you forget some stuff. So
yeah, because I mean, if we think of classical, like usual double categories, for example, when we consider, like, say bimodules or profunctors between categories, the advantage of considering such a double category is that we understand the relationship between functors and profunctors. Like there is induced profunctors, for example, from functors. Like
right.
So those are usually called equipments, I think.
Yeah, this is an example of an equipment frame double category, I guess you could also call it.
So is there like a, this is what I'm interested in actually. Is there a good, well-defined notion of the equipment property for?
Yeah, I mean, you could, I mean, it may not, you know, the consequences of it that you want are maybe not developed yet, but you can make the following definition: a double infinity category is, say, X is framed if I look at the source and target projection from X1 to X0 across X0, I want to say that this should be a co-Cartesian fibration. And this is, then you can prove that this is equivalent to the same functor is a Cartesian fibration. Or there exist, what are these called? Companions and conjoins, maybe?
Yeah, I think so.
And this is basically a condition on the homotopy double category, the homotopy double category without infinities. So, like the equivalence of these three things, if you remove the infinities, then this is the result of Schulman. And the proof basically is the same for infinity categories. I guess we wrote it out in this. It's probably in the appendix of a paper I wrote with David Geckner and Joachim Koch on analytic monads and infinity operads. But it's basically the same as the one categorical proof. You just want to check that these companions and conjoins allow you to define the Cartesian morphisms or Cartesian morphisms by combining them with composition in the double category.
Yeah.
But so this is so this small one of C is framed.
Yeah, kind of. I mean, this is looks like a fair definition. It's just that when I think of some like higher dimensional equivalent property, what I would like it to do is that also for a vertical simplex to have, for example, a companion, not just any vertical one simplex.
But I mean, it defines. I mean, isn't that just saying that they should be close in the composition, which they are because it's Cartesian fibration?
Oh, so you can. Okay, I see. Okay.
Like the thing that I guess has not been proved yet is that this is equivalent to saying you have like an inclusion of one infinity two category and another such that there's like
okay.
I don't think it's been proved that this definition is equivalent to like an infinity version of I guess Wood's original definition of an equivalent.
Yeah. Okay. Yeah. I see.
A non-expert question, but that's okay. So in the classical module theory, Morita equivalences are used to say the corresponding module categories are equivalent. There's also Haugseng cohomologies are equivalent, K theory, like there's classical applications of Morita equivalence. So what does these higher versions can be used? Maybe for differential rate algebras?
Right. I mean, you get the same kind of result characterizing module categories, and that's, I guess even classically you can generalize that to some statement about enriched categories. But maybe you can say, the infinity categories of modules will be like this is to some extent some work in progress, I guess, but at least the most, like for the most normal kind of modules, I guess it's probably known already, like that an equivalence of infinity categories of modules is the same thing as a Morita equivalence. Certainly it should be true generally. And then, I mean, things like Haugseng, homology, and cohomology, you can define in terms of invariant, you can define them in terms of this two category in a way that it's clear they have to be invariant under equivalences in this two category. So, you can define you can define the Hochschild homology as well, the what's the word I'm looking for? Like the trace, and like that's something you can define in any kind of like, well, certainly in any like some. It's an instance of something you could define in a general symmetric monoidal infinity 2 category, say, and it's if you think of it like that, it's must be invariant under equivalences in that 2 category, which is to say it's the Morita invariant.
Like in some philosophical sense, you're trying to understand the Morita equivalences of equivalences, or what kind of like kind of consequences would be.
I guess this case that I'm talking about would be more like doing kind of derived Morita theory and like doing it for DG algebras rather than just strict algebras. But then you can also generalize this to talking about well, this is one of these generalizations that I wanted to mention, that you can kind of upgrade from associative algebras to EN algebras, which is a way of defining things with n compatible associative multiplications. So classically, if you have 2 compatible associative multiplications, that's the same as having a single commutative one, but that's no longer the case when you go to infinity categories. For example, even for categories, you have having 2 compatible associative monoidal structures gives you a braided monoidal category, and then 3 or more give you a commutative one, a symmetric monoidal structure. And then if you're looking at things that live in an infinity category, this will in general be kind of an infinite family of different structures. And then you can define like, well, symmetric monoidal infinity n category. Say more NC of, but the objects are EN algebras, and then the morphisms will be kind of iterated bimodules in a sense. And so here this would be kind of the setting where you might think about things like Morita equivalences up to Morita equivalence, so to say. Like an equivalence between E2 algebras here would be like, you have associative algebras, and then like that give you an equivalence up to Morita equivalence at the next level. So
Thanks. Thank you.
Right. These structures are kind of also the ones that I'm, in terms of TQFTs, is more interesting to, you get higher dimensional things you can look at. And well, this isn't done yet, but there should be like a more general version where you have, instead of EN algebras, you have enriched infinity n categories, which morally should be the target for a lot of these examples we have of TQFTs.
Okay, so are there any other questions for Rune? Okay, so let me then thank you on behalf of the audience as well. Thank you very much for taking us through the world of infinity categories.